Hi students, this is chapter 21, Microprogrammed Control. So after we have looked at the hardwired control unit in chapter 20, so an alternative to that hardwired control unit is a microprogrammed control unit, in which the logic of the control unit is specified by a microprogram, or what we call firmware, which is a midway between hardware and software. We will start with 20.1 micro instructions. An alternative, which has been used in many complex instruction set computer processors, is to implement a microprogrammed control unit. A microprogram consists of a sequence of instruction. We call it micro instruction, and they are programmed in a microprogramming language. So it is a very simple instruction that specifies micro operation. As in a hardwired control unit, the control signal generated by a micro instruction are used to cause register transfer and ALU operations. Where are these micro instructions stored? So it is in a control unit, but in a special place called control memory. Figure 21.2 shows how these control words or micro instructions could be arranged in a control memory. The micro instruction in each routine are to be executed sequentially. So for example, if we have fetch cycle routine, so inside the fetch cycle routine, we have those micro operations, T1, T2, what do they do? And we have to follow them step by step. You cannot jumble up, do micro op 3 first and then do micro op 1. We also have other routine for the subcycle, also end routine, opcode, add routine, and each of these routine ends with a branch or jump instruction indicating where to go next. What does it mean? For example, maybe after fetch cycle, you're not going to indirect. After fetch cycle, you're using direct addressing. That means you are going straight to execute cycle. So what has to happen is that at the end of the fetch cycle routine, there is a jump instruction to go to execute. If there's no jump, it will force the micro instruction to go to the next routine, which is indirect, but that's not what you wanted, right? The control memory in this figure is a concise description of the complete operation of the control unit. It defines the sequence of micro operation to be performed during each subcycle: fetch, indirect, execute, interrupt, and it specifies the sequencing of these cycles. Let's look at this figure. Where exactly is our control unit? So you are familiar with all the registers in there, MBR, MAR, PC, and so on. We even have ALU and also clock. So the control unit is in the red rectangle there. So let's look deeper into that control unit. So what is actually in the control unit? We have more components. We have in the middle, the big one, that is the control memory, with all those routines. They are the set of micro instruction, and it is stored in control memory. Next, the input into the control memory is the control address register. It is equivalent to your program counter PC. So what is inside PC? The address of the next instruction, right? So same thing here. It holds the address of the next micro instruction to be read. Then the output out of control memory is what we call control buffer register, equivalent to MBR. So it holds the instruction itself. And lastly, we have the sequencing logic. Yeah, it actually, what does it say? A sequencing unit loads the control address register and issues a read command. Right, the one where when we want to fetch something from the memory, this is the task of sequencing logic. Let us now examine this structure in more greater detail. The control unit still has the same input, input into the control unit. We still have the instruction register IR, the ALU, flags, clock, and the output is still control signals, these two. The control unit functions as follow. The first step, right, to execute an instruction, the sequencing logic unit issues a read command to the control memory. This read command into the control memory. So this is step 1. Then the word whose address is specified in the control address register is read into the control buffer register. So this is step 2. Third, the content of the control buffer register here, where does it go? It will generate control signals. So here it will generate control signals and also the next address information for the sequencing logic unit. So both here are in the third step. And lastly, the sequencing logic unit loads a new address into the control address register based on the next address information from the control buffer register. So here, this is step 4. Bear in mind that all those happen during one clock pulse. The last step just mentioned in the previous slide needs more elaboration. At the conclusion of each micro instruction, the sequencing logic unit loads a new address into the control address register. That you know of. However, depending on the value of the ALU flags and the control buffer register, one of these 3 decisions is made. So first is the normal one, get to the next instruction. So add 1 to the control address register, still in the same routine. Or maybe you're at the end of that routine and you jump to the new routine based on whatever the jump micro instructions say. So maybe from fetch, you go to interrupt cycle. And third, it can also be jump to a machine instruction routine. That means to the execute cycle and follow what the opcode is. We have looked at micro instructions. We have also looked inside the control unit. So one of the components in the control unit is control memory. So how does this micro instruction is mapped into the addresses of the control memory? So this is the next section. Let's remember that a micro instruction is a set of micro operations occurring at one time. So if we have few micro operations occur at the same time, we call those micro instructions. So it can be one, it can be many. And the format are typically horizontal or vertical. We are focusing on vertical microprogramming, where each micro instruction will specify a single, it can be one single micro operation, or at most 3, a few. So at most 3 micro operations that occurs at one time. The other one is horizontal microprogramming, where each micro instruction specify many different micro-op as opposed to a single or a few, which is 3 for vertical microprogramming. We are going to be focusing on this vertical micro instruction. So they have 3 function codes. So these to specify 1 micro operation, yes, 2 micro operation, or at most 3 micro operation. Then we have jump condition. Yeah, it can be a jump condition or maybe branch. And lastly, we have micro instruction address. So this is the format of vertical micro instruction. Let's look at the familiar machine instruction and compare it with the new micro instruction format that you have just learned. The machine instruction format looks familiar. Yeah, they have opcode address, but they have one what is called I here, 1 bit I. Yeah. So what is that? That is to indicate whether it is indirect addressing or just normal direct addressing. The opcode can be, it is 4 bit here, and the address is, how many bits is that? So those are 11 bits, and these are some sample machine instruction: add, branch, store, exchange. You're okay with that, right? Now we are going to concentrate on micro instruction format. So F1, F2, F3, these are the micro operation fields that I told you about, where in vertical format we can have few, meaning from 1 or up to 3 micro operation fields, micro operation that we can perform at one time. CD and BR is our jump condition. And ED. Okay, now let us concentrate on this ED, which is address field. So if it's 7 bit, what does it mean? It means that in our control memory, so let me draw, in our control memory, remember the one in the middle in control unit, we have 2 to the power of 7, which is 128 words of control memory. So each is 1 word. So from 0, 0, 0, 0, 0, 0, 0 until 1, 1, 1, 1, 1, 1, 1. So in total you have 128 words from 7 bit to the power of 7. The 3 fields F1, F2, and F3 specify the micro operation for the computer. So we can have 3 micro instructions to occur at the same time. The micro operations are subdivided into 3 fields of 3 bits each. F1 is 3 bit, F2 is also 3 bit, F3 is also 3 bits, which means that each field are encoded to specify 7 distinct micro operations. So in total, we have 21 micro operations for 1 micro instruction. For example, if we have 1 micro instruction with 2 simultaneous micro operations, which means we don't have to use all 3. In this case, we are going to use only F2 and F3. F1 is empty. Here, 0, 0, 0, empty. So we look at the code, for F2. So from the memory to DR, so the code is 100. You can check previous slide. And PC plus 1, the counter, and we send it back to PC. This is 101. If you remember, this is T2 in fetch cycle. Yeah, so it occurs at one time. These two micro operations occur at one time. So this is one micro instruction with only two micro instruction field, F2 and F3. So F1 is 0. So therefore, the micro operation fields look like this. The next two field is CD and BR, yeah, condition and branching. So CD field selects the status bit condition. Yeah, this is the status bit condition. And what are BR? Branching. Yeah. What are the type of branch to be used? Jump, call, return, map. Lastly, we look at the address field. So the address field actually contains the branch address, meaning if there is a branching, where should we go? Remember our routine, we have different micro instruction routine. So at the end of those routine, yeah, step, it will tell you where to go, right? Either, let's say from fetch, we want to go to indirect. So if you want to go from fetch to indirect, so that address should be inside here. Yeah. So for example, let's say, what was my example just now? Fetch goes to indirect. Let's say indirect opcode is 1011. Right? So you because our address field is 7-bit, right? We have 128 words. And we have specified that there is a mapping bit. We have specified that the first 2 bit is 0 and the opcode bit is from bit 3, 4, 5, 6. Yeah, so this is the mapping and we put the opcode in the middle. So this will be our address, yeah, that we put in address. So if BR is jump, so we will jump to this address. Got it? Good. We're going to look at example of micro instruction using the vertical format. So we have 3 micro operation. Yeah, the maximum. And then we have the jump condition, CD and branching. And lastly, address of the first instruction in the routine. These are some examples of the execute cycle. Yeah, common one, add, branch, store, exchange. And then we have the familiar fetch cycle and also indirect cycle. We are going to look at the micro instruction of the fetch cycle routine. So there you have it. So you are familiar with the steps. So each line is at what? At T1, T2, T3. Please have your micro instruction field description in front of you in the previous slide. So in the first, yeah, at T1, there's only one micro operation. So one micro instruction have only one micro op. And that is 110. So go and look what is 110. Yeah, so exactly 110 is PC goes to MAR. So only one. Yeah, only one here. So one micro operation, PC goes to MAR in one micro instruction. So the rest, yeah, these are 0. Oh, let's erase it. Yeah, 0, no operation, no operation. And the second line, yeah, in T2, there are 2 micro operations. So we can have it in one vertical format. And don't have to do one by one, but our micro instruction can have 2 micro operation. The first one is, yeah, F1 is empty, no operation. But now we have two, F2 and F3. So F2 will be memory to MBR. That is 110. Is that correct? Check. Yeah. And then for F3, that is PC plus 1 goes to PC. And lastly, at T3, we have only one micro operation. And that is 101, which is MBR goes to IR. And the other 2 micro op is no operation. As for the conditional and branching, yeah, for condition for branching, it is 0, 0. So it is unconditional branch. So it always, yeah. So it is always, so look, 0, 0. Okay, this is interesting. Let's look at the type of branch used under BR. So there's no branching, yeah, in the first instruction. Second, no. The third one. Now this is why it is no longer 0, 0. Because after fetch, yeah, after fetch routine, so at T3, fetch routine ended, you need to tell fetch where to go. Do you go to execute, indirect? So we have to look at the address. So this is the address. The address is 0, 0, 0, means we have to go to this address, which is execute cycle, yeah, using the add routine. So I hope, yeah, you do understand, especially the difference between micro operation and micro instruction. So micro instruction is, yeah, a set of micro operation that occur at one time. In this case, yeah, very easy to understand. Yeah, this is 2 micro operation at one time, and we call it micro instruction. This is 1 micro operation. We can also call it micro instruction. We're going to do one calculation example. The question is, a system uses a control memory of 1024 words, and each word is 32 bits each. The micro instruction has 3 fields and a 16-bit micro operations. And these are the questions. Let's extract the main information and try to make sense of it. First, it says here control memory of 1024 words. What does it mean? Okay, it says that control memory. So why not we draw control memory? Suddenly, I love to draw. So we have control memory and the size is 1024 word. Okay, so it is 2 to the power of 10 and each word, so one word is equals to how much? The size is 32 bit each. Yeah, so one word is 32 bits each. Next, it says the micro instruction has 3 fields. So the address, the select, which is CD and BR, and of course our micro operation F1, F2, F3. And the size of micro operation is 16 bit. So if micro operation is 16 bit, that means select and address is also 16 because 32 bit each, yeah, each word minus 16 bit micro op, we get 16 bit. But this 16 bit has 2 components, select and address. So how do you know which is which? So select is 10 bit. Sorry, address is 10 bits. Yeah, address we calculated here. 1024 is equals to 2 to the power of 10. The same as here. So if address is 10 bit, our select is then 16 minus 10 equals to 6 bits. Yay, we solved it. That's it for chapter 21. And this is also the end of module 5 from CPU, pipeline and control unit. So students, go take a break and I'll see you in the next video. Bye.